Hey guys, in today's lecture we're going to talk about a technique for integration or finding antiderivatives called U-substitution. It's essentially the integration version of the chain rule for derivatives. It's not exactly the same as the chain rule, as we'll see, but it's very closely related. Now, before we get into the integration itself, let's introduce a topic that we kind of skipped over earlier in the semester called differentials. I've created this little animation here to show us how this works. Basically, we have a curve here, y equals f of x, and I just indicated a point on the curve, somewhere between 2 and 2.5, this magenta point right here. So you can see it right here. And as I animate through, let's see how these differentials work. So the first thing I want to do is take a step in the x direction, which we'll call dx. This can also be referred to as delta x. So this is just a step in the x direction. I made it a positive step, so I stepped over from this point between 2 and 2.5 in the x-coordinate over to about 3 in the x-coordinate. And this is called the differential of x, so dx. Now, it's pretty straightforward. It's just the distance between the 2 points that we chose, right? Or it's the step size that we chose. The distance between the y values of the point that we chose and then the point that corresponds to that new x value. So if we take this step delta x and we go up to the curve, we see that the height of this point is, it's around maybe 3.75, 3.8. It doesn't matter exactly what it is, but the point here is that the difference between the heights of those 2 points is called delta y. That is not the differential of y, so that's not what we call dy. To get dy, instead, what we do is we go back to the original point here, this point that we started with, and we draw the tangent line approximation. So this is obviously related to the derivative, right? We find the slope of the tangent line by taking the derivative. That's exactly what it is. And then we take the linear approximation by making the tangent line, right? The line with the slope given by the derivative that passes through that point. Now the tangent line intersects that vertical line that we drew over here at a different height. And we can see here as we animate through, that height right there, that's the differential. So the difference between the height of the actual point that we started with that we know is on the curve and the height of the linear approximation, delta x units away, or dx units away, the height of that difference there, that height difference in the y direction, that's called dy. So dy and delta y are not the same. dx and delta x are always the same, at least for what we're doing in this class. So dx and delta x are the same. We can think of it as a small step. Dy and delta y are not the same. However, as you make delta x very small, you can imagine this kind of vertical line moving back to the left toward this original point, and then this distance between delta y, dy, and delta y, this extra piece right here will get smaller and smaller and smaller. And so it turns out, by the way, that this is important in integration. So we've talked about integration as the area under a curve, and we take a Riemann sum, and we said we always use kind of a simple formula. We use the right endpoint formula for the Riemann sum. But look at here, if you want to measure this change in dy, let's call this point A, the x value A here where we selected our point, then how do we find the change in the height? Well, we take the unit step size times the slope, right? So the slope is the derivative of f, of the curve, at that point A. So f prime of A times our step size dx. And so dy is f prime of a dx. This is always the case here. All right? So this is a very brief introduction to differentials, but the notation of differentials is what we're really going to focus on. I think it's important for me to go through this little, brief introduction to what they are geometrically, but we're just going to manipulate this formula right here. We're going to take this formula and we're going to manipulate it. And you can see that this is not exactly what's in our integrals. Our integrals, when we integrate things, it's usually f of x dx. But this is very closely related, and you can think of antiderivatives and integrals, being the same thing as we learned in the fundamental theorem of calculus. So the point is, this form right here is going to be very useful for us moving forward. So let's consider an example. Let's just start with a differential. In this case, I gave us a differential dy equals x squared times sine of x cubed minus 5 dx. That's a differential. That's in the form that we just talked about. And what I want to do on this one is I don't want to plot it. I don't want to look at the geometry necessarily, but I want to think about what would happen to this differential if we make this change of variables. So let's swap out, instead of making this differential in terms of x, let's swap out the variable and make it in terms of u. And here I'm giving us the change that I want to make. So I want to use this u substitution where u equals x cubed minus 5. So the first thing is we just look at the formula that we were given. In this case, we knew what to choose for y. We were told what to choose for y. But what just turned red there inside of the sine function, that x cubed minus 5, that's going to be replaced with u, right? That's going to become u. So now our differential looks like dy equals x squared times sine of u dx. But that's a problem because we've changed the variable in one spot to become u, but we didn't change it anywhere else, right? We only changed the u that was on the inside, and we didn't change these other terms here, the x squared dx. Those are still in terms of x. So if we really wanted to make this change of variables, we need to get this in terms of only u. So to do that, let's look back at our formula for u. We've got u of x equals x cubed minus 5 here. And if we take the derivative of that, u prime of x is equal to 3x squared. So turning that into differentials, right, just using the formula that we learned on the previous page, if u prime of x is 3x squared, then du is 3x squared times dx. Another way that you can think of this is that u prime of x, another way to write it, is du over dx, right? Du divided by dx, and then you can multiply the dx to both sides. And so that's another way to get from here to here. I mean, I just gave us a formula, and we're just going to use the formula, at least for this lecture. But in general, you could make this a ratio of differentials and then multiply the one to the other side. But the point here now is that we can get a formula for du, something involving du, in terms of the stuff that we have in our formula, right? So we have x squared and dx in our dy right now, and we want to replace that. Here we have x squared and dx as well, but we also have this 3. So what we can do is kind of divide through by that 3, or multiply both sides by 1/3, and then we get this formula that 1/3 du is equal to exactly what is left in our differential that we didn't swap out for the u yet. So we can plug that in then, right? So we just make that substitution. And so our dy is equal to sine of u times 1/3 du. And actually, you can then just rearrange it. I just move the 1/3 out to the front there. But actually, that looks much simpler than the original formula that we were given, right? Our original dy in terms of x looked pretty complicated with this x squared, x cubed minus 5 inside of the sine function. We've reduced it by making this change of variables to just be a function of sine of u. Basically, dy is equal to 1/3 sine of u du. All right, for the next example, let's find an antiderivative, like actually find an antiderivative using this method. So here's a function. It's a ratio of trig functions. F of x equals cosine of 3x divided by 4 plus sine squared of 3x. So before we get into it, let's recall that we write this integral sign, this elongated s, f of x dx. If we don't put any limits here, right, if we don't put the boundaries on the limits, then this cannot be a definite integral. It can't represent an area the way it is because we haven't written down any boundaries for the x value, right? So when we write this down with no boundaries, this is called an indefinite integral. And really what it is just a symbol to tell us that we want to take the antiderivative, right? So this question that we were asked, find the antiderivative of this function, could be just rephrased as compute this indefinite integral, right? So let's write this down. And I'm just going to give us an idea on this one, and we'll do it. In general, as you do these yourself, you have to think about this step here at the end a little bit more carefully. But I'm going to give it to us for this first one. But here's our integral, right? It's the integral of the function that we were given, dx. And so my suggestion is let's look at this and try to write it in a form of something that we do know the antiderivative of. So my suggestion is to write it as the integral of 1 over 1 plus u squared du. Now, we might not be able to get it exactly in this form, okay? We might have some constants around, or maybe we even have to break it up and add or subtract or something, which is fine. That would be okay. But let's see what happens. So obviously the most important part of this, I mean, it's all important, but kind of the part that's going to be the more complicated part is turning the bottom into 1 plus u squared. So let's just look at the bottom term here first. That bottom term is 4 plus sine squared 3x, right? We want this to be 1 plus something squared. So we can factor out that 4. All right? When we factor out the 4, obviously we have to divide by 4 from this term. And at this point, we're really close. What's inside here is 1 plus something squared over 4. So really we just have to combine that and write it as 1, so 4 on the outside, times parentheses 1 plus sine of 3x over 2, that whole quantity squared. And at that point we see, okay, that's got to be our u, right? So our u is going to be set equal to sine of 3x over 2. That'll allow us to make this change that we want to make, which we'll actually do on the next slide. But before we do that, we also know that, okay, we can just make this change for the bottom, and that's great. But can we, will this help us with the top part as well, right? So on top we have this cosine 3x that's just kind of hanging around, and up until I, advanced the slide there, I had been ignoring it, right? Well, if this is u, then the derivative of this term is related to du, right? So du is the derivative of sine of 3x over 2, which is 3 cosine of 3x, still over 2, all times dx, right? And again, we can do the same kind of trick that we did last time, which is when we look at our integral, we've got cosine of 3x dx here, all right? We don't have the 3 and the 2, but we can easily multiply by the reciprocal there and make this 2/3 du equals cosine of 3x dx. So that this term right here we're going to use on the next slide when we actually compute this integral. So up to this point, we've done all of the housekeeping. We've made our observation, made a guess basically. We've done some algebra to kind of give ourselves the idea that yes, this guess will work. And now we need to plug this into the integral and actually compute the indefinite integral. So here's our integral. I just rewrote the same thing that we have on the last page, right? It's a little bigger now, easier to see. But this is the symbol that means for us to take the antiderivative. And we can now kind of rewrite this without making any changes yet, but just changing the form of it, changing the bottom so that it looks like this, right? So get it in that form that we rearranged on the last slide. Now at this point, the 4 has to stay here. What's inside here is going to become our 1 plus u squared, right? And then on top, that's going to become our 2 over 3 du, right? That's what we had for that. So we just make that substitution, and now look at this. This is much more straightforward. And we can then combine all these coefficients and move them outside the integral, all right? And then this could be written as 1 over 1 plus u squared du. And we know that 1 over 1 plus u squared is the derivative of arctangent of u. So this antiderivative here becomes arctangent of u. We keep the 1/6, right? That has to stay there. That came out of our computation. And then to get the general antiderivative, we always add this plus c term, right? This unknown constant. Now, this is great, except if we were asked to do this by, say, a boss at a job or something, and we were given this function up here, this little f in terms of x, and it has all this stuff, all these x's in it, and then we go to our boss and we give them this answer that doesn't have the x in it, just says u, the first question is going to be, well, where'd the x go, right? So to avoid that problem, obviously, we need to go back and we need to plug back in what this u should be. And remember, our u is this term right here. It's sine of 3x over 2. So all of that is going to go inside of the arctan function. All right, and so this is our general antiderivative of this function right here. And we did that by kind of thinking of it like an integral, an indefinite integral, and then making the appropriate u substitutions there. Now on this one, so that's our final answer. On this one, I have some recommended exercises. First of all, you should use trig to try to simplify this answer, because what's inside of here is the output, of a trig function. So there's an angle involved, triangle involved, we might say. And then arctan takes in that value and gives back an angle, right? So all of this can be simplified by drawing a right triangle and then carefully thinking about what all the parts mean, okay? So basically, try to simplify this one to get it in terms of just x without these two trig functions, the inverse trig and the trig function here. And then once you do that, go back to the original function and think, can you simplify this function at all in maybe a similar way? Can you simplify this at all in a different way than what we did? And then recompute the integral and compare your answers on those. So here's another example. This time we have a definite integral. So this example wants us to take the definite integral from 0 to 1/2 of sine inverse of x over square root of 1 minus x squared dx. So we're going to approach this the same way. We're going to look at this and say, which part of this do we want to make into our u? And so there's a couple choices. We could choose what's inside of the square root down here, but I'm going to choose the inverse sine function. Okay, so if we choose inverse sine to be our u, then the first thing that we should do is compute our du and see if it works, right? See if that helps. Because what we have to be able to do is our du has to be able to take care of all the rest of the x's here, right? We've seen in the first couple examples that if there's a constant left over, that's okay. But if it leaves any x's behind, we might have an issue. So the derivative of inverse sine is, of course, 1 over the square root of 1 minus x squared. So this is perfect, right? That means the differential is all of that times dx. And basically, now I've just broken this up into the two parts. Now we see that we have u times du, right? So that's perfect. So this integral becomes much simpler. Now I've done I've done something else here on these last two. I've written very clearly that in the boundaries of our integral, these are x values, right? This is saying x equals 0 to 1/2. And even when we changed it to u, right, we changed the integrand part to be in terms of u, we did not change these boundaries, right? Those boundaries are still in terms of x. So on these definite integrals, the next thing that we need to do is go back and compute, okay, we found out that it worked, right? The substitution that we proposed made our integral look a lot nicer. We need to go back and figure out what does it do to those boundary points, right? So how does it change the boundaries? So for this, you just plug in those limits, right? So when x equals 0, sine inverse of 0 is 0, so that one's still 0. But when x is equal to 1/2, the arc sine of 1/2 is pi over 6. So our integral now looks like this. When we change the limits, it's the integral as u goes from 0 to pi over 6 of u du. And now this is the one that we can just plug into. Once the variables are the same, you can do the fundamental theorem of calculus, take the antiderivative, which we know is 1/2 u squared, and then plug in these two boundary points, right? So plug in the 0 and then the pi over 6. I said that backwards, I guess. The limits go from 0 to pi over 6. You plug in the top limit first, then the bottom one, and you subtract them, right? And so for this one, you end up with an answer of pi squared over 72. And so that's how you do a definite integral using a U-substitution. As a last example now, let's look at another definite integral. In this case, we have the integral from 1 to 2 of x times the square root of x minus 1 dx. So let's choose our u. If we choose, really there's only two choices here. We could choose the u to be the x that's on the outside, but that's not going to change anything because u equals x is just changing the letters without changing any properties of them. So the other option is to choose u equals x minus 1. If we make that choice, then we have to go through our whole process that we've gone through this whole lecture, and we have to make the other appropriate changes. So we have to swap out du for dx. In this case, it's just it equals dx. So the derivative of x is 1 times dx. And then we already know that, from the last example, that we should change our limits of integration here. Really what we should do is kind of check and make sure that this change of variables works before we go into the trouble of changing the limits of integration. But it is going to work, so it's okay. So basically, these are the changes that we're going to make. Let's plug them now into the integrand. But I guess looking forward here, we can see that, yeah, the x minus 1 is taken care of, right? That becomes u. We've changed our limits, so they'll become the limits from 0 to 1. But then, and the dx is taken care of. But really, the x here is what's not taken care of yet. And that's kind of what I was alluding to before. So let's talk about how we can fix that. If we've got this x out here, and that's the only thing that's remaining. Well, depending on our choice of u, that could be a little complicated to change. But in our case, if we set our u equal to x minus 1, then adding 1 to both sides leaves us with x equals u plus 1, and we can plug this u plus 1 into the integral up here for this x. So let's see what that does. Yep, that just changes our integrand now to the integral from 0 to 1 of quantity u plus 1 times the square root of u du. And this is better than what we had before. And maybe I should have talked a little bit about why we need to use a u-sub at all on this one. Well, the problem here is that we don't know the antiderivative of the function on the inside, right? Maybe just looking at this one, it doesn't really look much better. But if we distribute through, so we treat this as u to the power 1/2, the square root of u, and then distribute through and just multiply it out, now we have not a polynomial, but a sum or difference of powers of u. So we can use our power rule for this, right? Now we just compute. So we apply the antiderivative power rule. We write our vertical bar there, that is the definition of the definite integral now. And then we plug in our limits. I didn't plug in the 0 because when you subtract out 0 to any of these powers, you just have 0. 1 to these powers is just 1 each. So actually, this is just the sum of 2/5 and 2/3. So, which turns out to be 16/15. And that's the answer to this definite integral. So that's the area under the curve, x times the square root of x minus 1, between 1 and 2. But notice we had to make all of these changes to make this, get this in a much simpler form, a much easier form to work with. But at that point, then we just applied our fundamental theorem of calculus, took the antiderivative, plugged in the limits. All right, so this is how we do U substitutions. I hope you guys enjoyed this lecture, and I'll talk to you soon.